This side, 0.2 millimeters, so it's easy to read.
The underside is still, it has the film. I have my glasses. I am protected. And there's still the film here, so it doesn't fall even. So this is one side of the glass window.
Careful.
Let's see how much I need to damage it. Okay. That's already better than this. Above all, not fast. Very slow. Otherwise you will get this. I do it a little bit closer to here, because then from the other side I can do it not exactly at the same place, so that the screws will not conflict with each other. And what you hear now is the sound of this external unit, which you know from the other videos of the heat pump and of the micro CSP, that this is inside the garage. It doesn't hinder me. With so many screws to turn in, it's also good to think a little bit about how to be efficient in the working. So, for example, you can put these screws already on their place, and then you can just work on. Now I want to try this hot glue. So let's see if this plexiglass fixes to the wood. I will try now. Oh, that's very good. That's really good. You can get it loose, but if you put it on many points, it will keep. We put this plexiglass on the table, but with the foil, the protective foil on the downside. Again, I connect the two marks of the cutter and I go 3 times, maybe a little bit more. Even if it is only 2 millimeter. Let's see if I put it in this way. Instead of so, I put it so. Let's see what happens. I think it will go deeper. You see the curl. I think it goes deeper in this way than in this way. You see the form? Okay. Don't forget the glasses. On the edge of the table, precisely. Okay, under. Okay. There's still some glue here. I have to take it away, otherwise I cannot put it. But okay, the measures are correct. I just take glue from here. So double side cutting. Let's see if that is easier to break, because such a small edge is really difficult to break. The glasses. Oh, that's very easy. Wow. So my new rule is do it from the 2 sides. That's a very clear cut. A new one. I put this first onto the previous. And then it should fit. Complete double glass. So this is its height of the air conditioner. A little bit below, but we will fill up on the 3 sides here. So this is what I made yesterday in the laboratory. You see it, the plexiglass, double glass, 4 centimeter of air, and here are the feet. And this is the space for the air conditioner. And I would close it with this board, which I cut, as you saw. And that goes here inside, and then I will make the form of the hi doggy Charlie. Do you want to help me? And I want to make a hole here in the form of this air conditioner in this board, and then it can fit here. And it will be airtight. And here is a double door. This is one side, and that remains open. And this is the door which will be closed. Yesterday I had also a little bit difficulty to put this feet inside this threshold, because the threshold is here higher and also here, so you cannot fit it inside, because also here there is a space, and you cannot get it inside from here and then also here. So you see that I had to saw away 1.5 centimeter here. Here you see it, and also there. And then it fitted, I could get it inside this narrow space, and then I put these blocks again there under, so that it will fit also, that will take up the full space from up to bottom. If we go away, for example, then I can put here blocks of plastic or so that will keep it in place. So you can do it as you want. Here you see the door which remains open, this door here. This is the door which you can close, and which you can go through. And you see that this is overlapping a little bit this new construction. And there we must apply this weather strip, because it's really a close fit. So this is the open door that remains open for all the time that this device is running. And here we see, well, this is glass, eh? You can look to it, you don't see anything. Okay, there's a difference. Okay, here is the wear strip. Okay, nice soft close. You can close the window in a normal way. That's not a problem. And even if this device is inside it, maybe because I foresee that this plane, so the back plane, will coincide with this plane outside, then maybe you can even close it when the device is inside. Yeah, the warm air which is coming out of here is sucked by this grill, and we don't want that. It must come from the outside, from the side grills. So that means I have just to close this grill here. Very simple, with a lid, with a piece of paper, just to try. We should be able now to test it. You can also see how I fixed this form, this board around the device. So I would just fill it up from the other side with the other foam in order to close all these gaps. But I really don't have so much time, so I just show you how more or less I do it, and then you can always improve it. Every situation is apart, and you have a little bit to improve and adapt to your situation. Charlie, are you ready for the test? Do you want to see if this works? And I will switch it on. There we go. And now it is in fan mode. And now I will just put it on one of the two modes, dehumidifier, because it is continue. Or you can also put it on the cooling mode, because inside it is maybe 18 degrees, and the minimum temperature which you can use as a set point for cooling is 16 degrees. So we can put it also on cooling mode and then decrease the temperature to 16 degrees. So the temperature goes to, and it starts working. And here you see now, hi Charlie. Yes, Charlie, that is the input for the warm air here. Here, this air is already cold. It comes from here. Now, and here is the warm air. This door is now closed. Here's the plexiglass, and here is the device with the closings here. So in principle, this is also closed, apart from some air gap, which I will close afterwards. The first number is the total consumption in the house. We have some appliances working. You can take maybe 200 volts from this, and then you have 670 watt or so. Let's say it's between 600 and 700 volts. And that is a way to separate the air streams that you don't have a short circuit between the warm air and the air which is expelled. Now, dear viewers, really this system working.
Unbelievable!
It is working at a very high efficiency, because here we have the air which is inside, which goes to the evaporator. That's at a very reasonable temperature, which will allow the evaporator, well, to let evaporate the refrigerant very easily. And so that will then, this heat from the outgoing air will then be given to the air which is going back from the outside here, from the sides, going into the condenser and then coming out of this hose. And now we are really working at a high efficiency, making heat, maybe with the COP of 3 or 4. And this is fresh air. This is really new air from outside, which is warm. Yeah, it is really warm, and it's fresh but not cold. We can also make a very rough estimation of the power of this device, because this anemometer had also a thermometer. And you see here the wind speed and the temperature is now 17.7. And if you know the wind speed and you calculate the surface of this area, of the output area here, then you can make a very rough estimation of how much air with which temperature comes out. So let's try. So here at the center we have 8 meters per second. Actually we have here 8.4 at the side. Here we have 8.3, 8.0, and here we have only 6 meters per second. So I don't know why this is. Maybe because it's okay, because it's a little bit bent, this head. But let's say we could calculate 7.5 meters per second, and the temperature has risen a little bit because this device needs a little bit of a couple of minutes of time, and we are now at 30 degrees of the air. So we can make an approximate calculation of the power which is flowing out of this. So this is a view of the home. So this is the plexiglass frame, double glass, and here's the device. And at the left side you see the double door, so we can get on the balcony. I want to try now also with the cold air. Six meters per second. Oh, there's only 2.5 meters here. It's not symmetrical because it's a centrifugal fan, and here it's 7 meters per second. And here again 2.5. So I would take here 4 meters or so. And the temperature is 6.7. Yeah, centimeters are 12 centimeters by 6. Well, here it is less, it's 4 centimeters. Here it is 7. So we must make an average of it, and this will be the same. Here we have 6 centimeters by 18. You can even fill it up, this space to fill the gaps here with this volume, which was the protective foil of this plexiglass. I managed to put the start waveform of the air conditioner on the screen. So here is only the fan is running, and it's very low consumption. Then at some point you have start, and it is so this is up and down. It's one period. That is 1, 2, let's say 5 periods times 20 milliseconds, and 20 milliseconds is written here. Those 20 milliseconds is the horizontal division that you put here. So you can change this, and then it becomes smaller. And you can study it better if you change this. Okay, then you have really from the whole transient effect is from the start to the end. And that is, okay, 1, 2, 3, 4, 5, 6, 7, 8, and that is, so 18 divisions times 16 division. It is 116 milliseconds, so 1/6 of a second is now on the whole screen. And you know, as I said, one period is one up and down, and that's 50 Hertz. And you see that one period takes 22 divisions to 20 milliseconds, and that is 1/50th of a second, and that's corresponds exactly to 50 Hertz. So then you see that in 100 or 1/10 of a second, you have this whole transient, and then the current is to normal, and the normal is, well, it's more or less 600 volts, and then you are at more or less 1/2 division. Okay, that should be nearly 3 ampere. So, and here we are at 2.5 division. Okay, I mean 3 ampere is then RMS, but in reality, if you have a sinus, then the real value is of course higher. But what I'm interested now is the ratio between the proportion between here, and that is more or less 6 times, 6 or 7 times or so, because here we are even get at 3.5 division, and here's half a division. So you can say that the current is for 4 periods of 20 milliseconds is really at this peak value of 350% of the normal value, the current which is taken up by this air conditioner. Okay, then I will show you how I set up this trigger event, because usually you have this oscilloscope, they use it for cyclic events. So then you have, for example, you take a current that's going on, it's just 50 Hertz, and then you have the trigger you have in automatic. Well, I'm not here to give you a complete course on triggering events, because there are many videos about oscilloscopes, but I just want to show you how you can visualize the starting current of a device, how high it is. So I will just focus on the triggering sequence, how you set up this device. So we are at channel yellow, so channel 1, and then you have here this voltage lets you change how big you see this event, and even if you have this, you photograph this event, you can still change this also afterwards. So it's not only at the moment that the event must still happen. Then here you have the position. So we put it at 0 because we have really a sinusoidal event. It's alternating current. What I want to show you how we start this air conditioner and how we set up this as an event. So what we do is we put the menu of the triggers, of the trigger event, and we put it on channel 1. We have it already, and we have here single mode. We have here an edge. That's not so important which edge, the falling edge or is the rising edge, and here's the falling edge, and you can change that. So you can change it here, and then you see that it just chooses the other edge here. So we have a single event, we have a single edge, and we have the source is channel 1, and we have the mode is single. Well, you can put automatic, and it goes always back to automatic, and then you use the event. So you don't see the event now anymore. So now we have to make it a game. So we go to single event. So we push here on the mode, and then it goes to normal, and then it goes to single. And then you see here the green button, and that means this is now ready. And I can do in this way stop, and that you must not do it. It's now red, so it doesn't do anything now anymore because it is just frozen. So now it is on ready, on the green, it is ready for triggering. The triggering, you see here the arrow, the yellow arrow, that it is moving now. And then you just say, okay, I want a rising edge, and I know that the current will go up to 3.5 division or so, and then I can put it somewhere here where I know that it will arrive. And then here you see a small t, and that means that the event, the moment that it will trigger, it is here. So if you want, for example, to see the waveform, that it starts here and then it goes on and then it goes back to normal, then you must do it in this way. But I want to give it a little bit of space so that we can really see where it starts. So I move the position. So this the triggering position. The horizontal menu here is, if I take the position, then you see here the T, the trigger, will move here. So I know that now the start of the trigger will be here. So if the event will start at this moment here, that it goes beyond this value, the voltage, then it will be here. It will start tracing. Okay, so now we can start. Air conditioning. Just check that it's still okay. Now it's going in auto. So I really must check that this is always at single, because it goes back to auto if I do certain things. I will start now, and there it is. It was just waiting like a spider in the web, and at the moment that it goes off, then it stops, because it's one single event, and if that event is over, then it doesn't continue to trace. So that's the reason that if you have one unique event and that will not repeat, then you must put this trigger on the right place so that you see everything. So at this moment I can change the visualization. For example, the scale here on the horizontal menu, I can change the scale. I can change also here the scale. Okay, but that is the way how you set up a trigger for a single event, and I find that one of the things that I don't see so much information about single event triggering, but that is really very interesting. I like that. Also for all these events, these starting events, which you can visualize on an oscilloscope. And I find this really very fascinating, that you have this information that you can just see in reality how big this current is, the starting current. So you go from 5 times bigger than the normal current. I didn't know how many cycles it took to start. So now I know that it's 5 cycles that you need to start, and that's 1/10 of seconds. I will now explain you how I took this measurement. So I have here the current, the voltage, the cable from the grid, which is arriving here. And then it's going to this device, to the air conditioner. But first it is going, one pole is going to here. And be careful, because in this moment there is this 230 volt is here. So these are things that you must know what you do, because it's dangerous if not. So here you have 2 resistors of 1/2 ohm, and they are in parallel. So I have now 1/4 of an ohm. And why do I use this in parallel? Because in that way the power is divided between two resistors, and the starting current will not cause too much heat, because one resistor is 5 volt and two resistors in parallel are therefore 10 volt. So that is, you can calculate how much power there's consumed in a resistor of half an ohm. That's just half times the current in a square. So 3 ampere is the normal current in this air conditioner, and then that to the square is 9, and then you have 4.5 volt if you would take one resistor. That's with the normal current, and if you have a starting current, it's of course more. Well, okay, we now know that it's 100 milliseconds, so it's not so much, but just to be careful, I took 2 resistors. Okay, then it's going back, and then you have the normal circuit as if this was directly going to here. You know that if you have a 4 ampere, for example, now in this case it would be 6 times 3 ampere, that is 18 ampere, so that's really some current which is going here. So then you have 18 amperes times a quarter of an ohm, and then you have the voltage which you will have here, and which is really the voltage that you are putting here on the screen. So that is 4.5 volt. It means then you have to put 4.5 volts here on the screen, and that's the reason that you have then to put this scale here. So we are at the yellow channel 1, that is the yellow value here. You see here 2 volt per division, and that's the reason that you have to put that in this way, 2 volts per division, and then you see everything. And that's all. So you just convert this current which you want to measure. You convert it in voltage in this way. So it's a tiny voltage, it's much smaller than this 230 volt. You convert that in a voltage, and then it's the voltage which you put on the screen. That's the way it is for an oscilloscope. So I hope that you like this experiment, and now you know how to use this instrument to visualize what is happening at the start of an air conditioner. And this oscilloscope is sold very much, and you can also buy it for not too much money, for $190. It has much more possibilities than what I had 40 years ago when I started as a student to use these oscilloscopes. And it is also so very light. And what I do usually when I work with the 230 volts, where you have also, of course, the ground, because these devices have a ground, and just to be sure, just to stay on the safe side, I put the power supply, I put it here on this device here, which is the EcoFlow, and which is 250 watt hour of energy which you have in this small little box, and it can give 500-600 watts of power supply. So not for this air conditioner, please. But okay, it is of course completely off the grid, and so you don't have problems with the ground. And that is normally a thing that they warn against, that you don't create a conflict between the power supply, which might have a ground, and the ground of the consumer device, which is in this case the air conditioner. So in this case you have absolutely no ground, no conflict, and you just run it at an eternity, because this is consuming so little Let's see how much it consumes now. Oh, that's not much. That's 6 watt. So that means you can go on 20 hours with this oscilloscope. Okay, so that is 2 things which I can say to you that I'm very happy about, that I bought it. This oscilloscope, and then also this EcoFlow, which I use also in the case of a blackout, because you can run also our refrigerator, which is an inverter type and which consumes 40 or 50 watt. And that you can certainly do with this for 5 hours on this EcoFlow.